Let me introduce our Tech Talk speaker today, Patrick McFadden, who is from the company DataStax, who is one of the primary drivers behind the Apache Cassandra project. Patrick is actually the chief evangelist for Apache Cassandra at DataStax, and he's going to talk to us about Cassandra today. So let's give him a warm welcome.
Oh, thank you. Wow. So the first thing I like to do whenever I do a big tech talk is get a group picture. Here we go. Hang on. Because everyone's going to be like, you were in Kansas City and you had that many people, I'm going there. Because I've never been to Kansas City before. This is my first time. And this is really cool. I think this is the biggest tech talk I've done in about 6 months since a summit, like a big event. So I'm really excited. You guys are awesome for coming out today. And so, so I'm Patrick McFadden. I'm chief evangelist, which is really cool because I get to wear robes sometimes. And I'm also a solution architect, which means I get to do stuff. So I don't get to just say stuff, I get to do stuff. And that's important to me because I'm an engineer. My background is engineering. I'm a computer engineer. My background's in distributed systems. So I'm not just a talking head, mostly. Depends on who you talk to. But I can talk to you about how to actually do this, and I have done it. I've been using Apache Cassandra for years and have probably implemented some of the bigger clusters online right now. So I'm going to go through my slides, but afterwards, if you want to ask me questions, hit me. I don't care what you want to ask, unless it's something personal, and I probably won't. But if you want to ask me questions that are really in depth, let's go for it. And remember, don't do anything proprietary. I don't want to hear it. So this talk is going to be an introduction to Cassandra. Now, this isn't just a fluffy talk. It starts out a little fluffy, and then we just get right into it. But I'm going to kind of set you up a little bit, make you feel like, oh, this isn't going to be so bad, and then I'm going to really hammer you. So you better get your thinking cap on. Everyone had coffee, right? That dude didn't. All right, get him some coffee, quick. So 5 years of Cassandra, and surprise, surprise, I showed up around, I think here. Hang on, I got my magic laser. I showed up around here somewhere, and it was crazy back then because Apache Cassandra started out at Facebook, of course, but it really didn't turn into something until it became an open source project. And since then, we're now on Apache Cassandra 2.0. That's in the trunk in Apache, and that's an amazing amount of movement. And I bet you if I was to log graph this, it would look like a straight line because we went from 0.1 to 2 in 5 years. That's pretty fast. So find your favorite company. I love logo slides, don't you? Because you're not going to you probably found one, and it's not your company on here. Let's fix that. You know what's really cool about this little side bit? One of our engineers actually makes this. He wrote I think it's some Python code to go out, find a list of everyone who says they use Apache Cassandra, go find their logo, scrape it, put it into some file. Crazy. I mean, there's a nerd behind this, which I think is really cool. And marketing people still can't figure out how he did it. So why Apache Cassandra or any non-relational database? Because I think this is where we're at in 2014. And I can finally start saying that without saying 2013 first. So I'm doing the checks right. We are at the point now where I think everyone's kind of on board with the idea that this is a viable technology, but why? And it's because the world's changed, right? We are definitely more connected. Everybody's got one of these, and it's not going to stop. Some of us have more than one of those, and we're just generating an enormous amount of data. Think about every picture you take. I mean, I looked at my phone. I have 2,000 pictures on my phone. How did that happen? And it's just because we're collecting a lot of things, and we're pack rats by nature, and we don't get rid of anything. So the nature of us humans is that we are going to be more connected and be more pack ratty, and so we have to deal with that problem. So we're also a lot less tolerant for problems. And I don't know if you could see that, but this might be near and dear to you guys. I mean, healthcare.gov is a great example. I mean, that was a big public example. I've been doing web work since the 90s, And I've been involved in so many epic failures in web launches that I can't even count them, either fixing them or watching them happen. The fact that healthcare.gov happened, everybody in my field was like, yeah, okay, that was the first shot. Should have had a beta period. But what happened? It just became a problem. For the first time in U.S. history, a president went in the Rose Garden and apologized for a website. That's crazy. This is the world we live in now. And, you got these guys that are talking about it in Washington, D.C. now. This isn't just an internal problem. This isn't your boss going, hey, how come we're getting a lot of 500 errors on our website? So as a people, we've become less tolerant for problems. We expect 24/7. Just like when we pick up the phone, we expect dial tone. Or when we turn it on now, right? So we have a lot of traditional solutions that have been out there. And I'm sure this logo slide, you probably have one of these. I've worked on every one of these, a lot. I've been an Oracle DBA, SQL Server. That was my young days. I needed the money. But IBM DB2, I worked on DB2 on mainframes. Maybe aging myself a little bit. But all of these technologies work great, work just great. But then as we have progressed through this, what we're doing right now, it's really not turning out to be the best fit, right? Especially with some of the things we're trying to make them do. And we still try. There's our good buddy Larry. And, Exadata. I love Exadata, the way it looks. I wouldn't want to buy one. I almost bought one. It was really pretty. But it's still a single box. And we're trying to vertically scale ourselves into this. And if we can't vertically scale, I was stuck in this hell for a while, shard hell. And so we were trying to come up with these ideas as early as like 2002, 2003. I remember when Memcached first came out, I thought it was going to save the world. Kind of did for about a year, and then things changed again. So we're constantly trying to fix this problem. So what about that? Well, we kind of needed a new plan. And what I say is we need to do some computer science. I do not believe in hacky projects. I'm a computer scientist, an engineer. I believe in that. And there is a lot of that applied to this problem now. So let's talk about this briefly. So the Dynamo paper, 2007. Wow, that is almost big enough to read. That is crazy. All right, so Dynamo paper was crazy cool because what they did was this is Amazon. They're like, hey, how do we stay online all the time? This is a shopping cart problem. And this is kind of immortalized now, the Dynamo paper, because it's the basis for a lot of things. Actually, even databases that don't implement what was designed in the Dynamo paper, there are still influences from the Dynamo paper. And it's all about how do you keep things reliable, performant, always on. That always on experience is where Amazon was. Jeff Bezos says, I want money. Do not let my shopping carts go down. So he put PhDs on the problem. And this is where the Dynamo paper came from. The thing I really like about the Dynamo paper is going to the very back. 24 papers cited on there, going back to the 70s, from companies like IBM and Digital Equipment Corporation and Xerox PARC. There's really cool science in that. So it's not just made up. It wasn't like they went into a room and had a whiteboard session. They actually applied real computer science. So Dynamo paper, 2007. I'm going to go back a year, but it's not as important. Big Table, 2006. How do you make a rich data model in this distributed system? Highly performant. This is a big problem that Google had. Google was trying to take over the world. And with this Nest acquisition, they finally succeeded. They got my house. So Google has been great about publishing papers and then everybody trying to figure out how they did it, right? Hello, if you got, you guys are a Hadoop shop. You got MapReduce. Well, thanks, Google. Well, Big Table was very interesting paper indeed. And if you use HBase, you're also using Big Table there as well. So along comes Cassandra in 2008. Cassandra was a blend of the Dynamo paper and Big Table. And it took the distributed nature of Dynamo, and it built the data model using Big Table and the storage engine portion, combined them into what the two guys that wrote this, Prakash and Avinash, that this was going to be a better plan for what they needed, which is a highly available data store with a rich data model. So it started out at Facebook, and of course there's lots of folklore about that. But really, the time that it became its own is when it went to an Apache project. And I know that you guys do a lot of open source here. You know how it is. Once you get to Apache, you got your big boy pants on. It's time to go. And then that's when it really took off. And you'll see February 17th, 2010. February 17th, by the way, my birthday. Happy birthday to me, because that's when it started. And you'll see that if you look at the commitments and things, the committer graphs, that's when it really launched. And since then, it hasn't even slowed down. It's probably one of the fastest moving projects on Apache right now. So what about Cassandra? What is it all about? So again, since the roots are in the Dynamo, it's all about this more than one server. It's clustering, it's a clustered system. So every single node is independent. A node being a server, a VM in the cloud, but a node is independent. It shares nothing. So memory, disk, everything is independent. And when you have that, each node then is responsible for a certain portion of the data set. By that, it's able to do more capacity, meaning like linear capacity planning. So if you need more capacity, you add nodes. So if I need to double the capacity of my cluster for storage or speed, I just double the number of nodes that I have. And this gets proven over and over and over again. Here's one of my favorite graphs. This is from a VLDB conference, University of Toronto. They took a lot of data stores, did some testing to see how they scale over different models. And again, Cassandra showed that linear scaling. That's a nice straight line. Add more nodes. Well, that's the way it was designed in the Dynamo paper. Basically, they keep proving the Dynamo paper over and over, which is cool. And I'm working with McMaster's University to prove this yet again. They contacted me, but this is going to be done again. But it's really, I think this is an interesting project for distributed computing geeks, because the Dynamo paper was really a great paper to see, and then to see the implementation is like dissecting a frog. That's kind of a weird analogy, but anyway, they get to see it in action. They can actually do it instead of having to build it themselves. So the other thing that really makes Cassandra desirable for people who write applications is the distributed nature of the system. I'm going to go in depth in this a little later, but what you're looking at is really how, I think this is the killer feature that is really the only thing that Cassandra has right now. It's the differentiator. It's the best game in town when it comes to replication, because it's asynchronous replication, not synchronous replication, which fails. No masters, no slaves, no elected leaders. And when you have this type of setup, we have plenty of users out there, and you've probably heard them talk endlessly, like Netflix, doing active-active. There are multiple data centers, and they're active-active because they can manage their data in a way that's reliable and consistent, but also this is just out-of-the-box functionality. It's hard to turn off replication. That's one of the funnier questions I've ever gotten. How do I not replicate? I don't know. It just wants to replicate, and that's the way the system is built. And yes, that's a WAN link from East Coast to West Coast or overseas. And that's probably more common now because a lot of global companies, they want to have multiple data centers around the world. They need to synchronize their data. So let's take a look. Oh, here's my cheesy graphic. I'm really bad at graphics. I'm really good at code, though. Let's look at this single node. So we're talking about a cluster, but let's drill into that single node. And what I want to do here today is I'm not going to try to give you every single detail about Cassandra, or you guys could participate in one of my all-day seminars. I want to look at some specifics to give you a taste of what's in there, and in more technical detail. So first thing I'm going to look at is writes on a single node. So a single node, like I said, shared system, each node is going to be independent. So if we look at the writes on one node, we could just hit the stamp and multiply that thing out, right? So I want to look at that first, and then we're going to talk about how that works in the cluster. So when a client writes, sorry for the fuzziness of that, When a client writes data, and here is an update user set first name to equal me, where ID equals P. McFadden. So this is a pretty standard user table update, right? I want to change the first name of this dude, which just happens to be me. So when the client writes that, here's the Cassandra server portion. It's going to write what's called a mutation. Now, I know you guys do a little thrift here. There you go. That's a thrift mutation. Right now, we're starting to move away from thrift, but it's still a pretty accurate way of describing what you're doing here as a mutation. And that's going to be, it's going to say, here's the table, here's the row key or the primary key, which is the ID P. McFadden, and then the column with the value that I'm going to change. That's a mutation, right? So when that arrives to a single server, first thing it does is it writes it to the commit log. That's your durable portion. And I feel like that's not optional. Because when you write data to a server, I want it to stay there. When data disappears from my server, I get really antsy and probably don't want to use it anymore. So writing it to the disk is a good idea, right? So that's the first thing it's going to do. This is an append-only log, so it's very fast. If you're using spinning disk, that single spindle with a disk head is not going to be moving around. It's not going to be doing random seeks. You're going to have a disk head sitting right there, just clicking, click, 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 as you do appends. That's what makes this really fast on an insert. And now, once it goes to the commit log, it then puts that into a mem table. A mem table is a structure. It's based on a table, users, and it's, the mem table is identified by the primary key right here, which is P. McFadden, and then it's going to have all the columns of data. And there can be several columns in the storage row. As a matter of fact, 2 billion of them, if you want. That came from Bigtable. And so what this mem table is going to represent is that row of storage data that I'm going to have. And so that's stored in memory first. So now I can acknowledge it back to the client. Round trip complete. So that's a very simple write process. And that's one of the things I love about Cassandra is just the drop-dead simple write path. It's easy to figure out, and it makes scaling a lot easier when it comes to this. There's no adulterations in here. Although we just introduced triggers. Anyway. So, but there's nothing in there that's going to stop this from happening. And this is one of the reasons Cassandra when it was first started, was so stupid fast on writes. And now it's stupider fast on writes. And it's because of just this very simple process. So what happens after acknowledges it to the client? And you're not just going to put this in memory. It's not an in-memory database. The next thing that's going to happen is as those mem tables start to fill up, there's a flush process. And that flush process writes out the mem table to a file called an SS table, a sorted string table. And so this sorted mem table being flushed to disk is a sequential write. Now that's a very different kind of I/O operation on your hard disk, where most relational databases, now like I said, I was an Oracle DBA, I spent all my days chasing IOPS because everything was random. Random reads, random seeks. And when I talked to EMC, they're like, dude, I can give you all the IOPS you want for whatever money you got. But that was the name of the game, is random I/O. Cassandra's not about random I/O. It's about sequential I/O, which makes for a very different type of game when you're doing server implementations. So the sequential write also, whoops, get back. Laser, there. That sequential write is putting something in order on disk as well. So when I ask for it, and this is part of your data modeling that if you were to do this, you think about how that works. And this is actually built into how Cassandra writes data, is that order is preserved on disk. So when you ask for it, it comes out in a sequential read, very fast and very quick. This is one of the reasons time series data is so good with Cassandra. Because when you put something in time series, it's going to be ordered by time, the temporal order. And when you ask for it, you're probably going to ask for it in a slice of temporal order. And it'll pull out in one shot. Less seeks on disk. So you're going to get things in microseconds instead of milliseconds. So what happens later? I have a situation here, and this always comes up. What happens whenever I change my first name to Patrick, and before I had the same row of data with Pat? Okay, that's pretty interesting problem. So I had originally put in just Pat as my name instead of Patrick, and so now I have potentially duplicate data in the system. Since this is a write-only process, and I should mention also, this sequential write, once it does the write of the SS table, that's immutable. It will never write to that file again. It's done. And that also minimizes the amount of random I/O that you have to do. You know, DB files, like in MySQL and ODB, those files get thrashed, right? Because it's constantly rewriting the pages inside the file. You never have, once you write an SS table, it's done. Well, if that's the case, then we have this problem. The first time it wrote the SS table with this older timestamp, that's the data that was there. Now I rewrote it, I put Patrick in here, and now it's got new data in the same place. Oh, that's a problem. Well, a couple of things here. First of all, Cassandra's always going to look for the newer timestamp. The last write wins. It's very simple. And so it's going to give you the right data, but the inefficiency is that there's two values in there that it's going to have to pick from. So how do we fix that over time? Compaction. Compaction is a really interesting process because, again, very different from what you've been used to in a traditional database, relational database. It takes those SS tables, it does a sequential read back into a mem table of both files, does a merge sort, picks the one with the latest timestamp, and when it finishes that, it writes out a brand new file with the merge sorted data in it. Along the way, it also gets rid of things that has been deleted, old data, that sort of thing. And then writes out, so we do a big sequential read, we do a big sequential write, and then it just deletes the old files. So what you'll see from an operator standpoint is you'll see your disk space going up and down, up and down, up and down, perfectly normal. And it's because of compaction. Compaction is if you get into Cassandra, you'll learn some words that everyone else has in their vocabulary, like the word compaction. And it's just part of how you run a server. Really what we're doing is you won't get away with having zero I/O on a box unless it's in memory. And with relational databases, you're front-loading a lot of the I/O early on. And with Cassandra, you're backloading it. You're saying, I'm going to defer some of that I/O till later because I want fast reads and writes now, and then the efficiency will come from the compaction. So it's rearranging the order of when I/O happens and making it more efficient because it's sequential I/O instead of random I/O. But in this case, you do get the right data. So how does that translate to the cluster? So that's a single node. I just wrote one thing to a node. Of course, that's not going to be a big deal. That's going to be a big deal if I have to scale out to 1,000 nodes, right? So when you're fully distributed like this, there is no single point of failure. And it's all about how we replicate the data. Now, if one node has the data and it goes down, that's a no-brainer. You just lost all that data. Part of the Dynamo paper was all about how do you distribute data efficiently and consistently, just knowing that failure is going to happen. I always ask this question. I'm still waiting for a positive answer. How many of you have never had a machine failure? Ever? Never. It'll happen. Machines go down all the time. If you're in Amazon, they go down all the time. So what's funny is that the Amazon engineers who had the crappiest hardware are the ones who had to figure this out. Because like, man, we can't fix our infrastructure. We'll just come up with a new plan. So, and actually, this is one of the reasons I started to really love Cassandra, because before I worked at DataStax, I had it running in production. I had it doing a lot of collection. It was watching students log into systems, and it was one of those things that it was a back-end process, very, very critical for what we needed to do. I had it running in Amazon. This is I love Cassandra, I hate Amazon story. And it was distributed across multiple availability zones in Amazon East. that weekend, there was an outage in one of the AZs. It was AZC or something, EC. Went down. I didn't know about it until Monday. I came in, I'm like, why are these nodes gray? They're not even there anymore. Huh, okay, we'll spin them up in another AZ. Never had a problem. Now, if that was one of my fat Oracle databases that was running up there, you bet I would have been getting pages. Nagios would have been flipping out because that was a single point of failure, right? It would have been, bam, that would have been it. I would have been up at Saturday night, and that's when it happened. It was a Saturday night. Thanks, guys. And I knew people that had been dealing with that problem. Some friends of mine at Instagram, they were up all night. That is a problem in the 21st century, right? You have a lot of infrastructure that has to be managed. Don't make it that hard on yourself. And so with this fully distributed, no single point of failure, you're giving yourself an edge. But what else do you got? You're giving your customers a little better experience too, because nobody knew that there was any downtime. And I certainly didn't, because our websites were reporting everything was fine. But users are very intolerant anymore. And 10 minutes of downtime, an hour of downtime. Now, granted, with Instagram, I think the tweet the next morning is like, millions of people have no way to document their breakfast this morning. Okay. Got to keep it in relation, right? But still, that if you're doing something mission critical that you're making money from, how's this problem going to help you? So how does this work? It's about partitioning and how a primary key is done. So a little bit of computer science here. So we have a primary key, and this is an example table. The primary key would be the first name of the person. And I'm going to walk you through the process of how we distribute data efficiently. So primary key is the first name of the person. Granted, not the best primary key, but it works, right? So each row of data has age and what cool cars they're driving and their gender. And these are sparse tables, so you may not everyone has a car. So the primary key is what we use to find placement. How that works is we do hashing. We use MD5 or Murmur3, and we hash the primary key into a nice, neat 128-bit number. Consistent hashing, unique number. That's important, because then every time we want to look for that particular key, we get a consistent hash of that key. So how does that fit? Here's our token ring. Anyone who's ever worked with IBM products before will laugh at this being called a token ring, but it really is a token ring. Why do we call that? Well, here's my 4-node system. I'm going to color code it. And how I'm going to build this is, so I have a 128-bit number that I'm going to break into 4 chunks, okay? So I don't know how good your 128-bit math is. Trust me, it kind of looks like this, right? So we're going to take that 120-bit number and break it into ranges of equal parts. And so that means that for a range, 120-bit number range, we're going to have each node is going to be responsible for a quarter of it. So whenever we hash, say, Jim, we say, okay, here's the MD5 hash and 120-bit number. It fits inside this range right here. Consistent hashing, we know where it's supposed to fit. It'll drop onto node C. Carol, she goes on node D. Johnny's on node A. And Susie's on node C. So because we're using MD5, it's somewhat random. So you get a good distribution of your data across the ring. But it's also consistent, so the client doesn't have to ask. It just says, here it is. The other thing that's really cool is we get a leg up on things like when we do replication. So how does replication work in this case? So if I was just spreading my data around the node, around the cluster, and each node had one piece of data, that would kind of suck when node D disappeared, right? And it did that day for me. But how do you make sure that you wake up Sunday morning and not have an emergency on your hand? Well, this is where the replication comes in. So what we're looking at is each node has, when we set what's called a replication factor. So let's look at replication factor of 3. Replication factor of 3 means that we have a primary node, which is that first range, but it also has replicas that are responsible, that will be maintaining the replica of that data for the primary node. And each one shares a little bit for each node. So that means, and it's, again, consistent, so that node D, the adjacent clockwise, 1 and 2, are going to have that data. So here's a replication of 1, 2, and 3. When the client writes the data, it will go through a coordination phase, and it will write all 3 at the same time. So how you do that is about consistency. And that's how you maintain, this is how you can maintain your system in case it goes down. So when you're writing to 3 copies is good. You can do it as any way. You can set the replication factor to 4 in this case. You can be fully replicated. Or you can set the replication factor to 2. Be a little more cowboy. But it's up to you. And the consistency, which I will be talking about in a little bit, is how you as a programmer, architect, feel good about that data being in your cluster. Because, again, this is your data. Being cowboy isn't cool because you got to explain to your boss why you're such a cowboy about this. And so we have, this is the other part of this. So I'm going to add one thing here. If you go into any talk about Cassandra lately, in the past year, this model right here is very simplistic when it comes to nodes. Each node would own a token range. Since then, we've gotten a little fancier, and we're moving into virtual nodes. This is actually part of the original Dynamo paper. And the virtual nodes are just simply that we take each physical server and we chunk it up into smaller pieces. Each node we have smaller ranges, and they're non-adjacent ranges. And the reason we do this is there's a lot of efficiency we can gain when we add new servers and decommission servers from the cluster. It allows for parallel writes and parallel reads. Decommissioning and bootstrapping is a runtime operation. That's when you bring a new server into the cluster. As a matter of fact, there's some demos you can watch on YouTube where Netflix got up on stage and doubled their cluster live while they're talking and doubled their capacity right there on stage. That was pretty cool. And I'm really glad it worked. Because I was like, you're really going to do a live demo on stage? All right. That never works, right? Oh, I lost my internet. But no, it actually worked out pretty good. And it was a cool demo because you could see as the writes per second are going into the cluster, as it's adding 200 gigs worth of data into those new nodes, all of a sudden the response rates go down, the amount of data goes up. It was pretty cool. And that's the way it was designed to work. And that's why companies originally that looked at it like Netflix were all about it, because they have that problem. Because I bet you almost everybody in this room watches Netflix on a Friday night. I bet you're not watching it on a Monday afternoon, though. So their performance problems are based on you, the viewer. So they have this problem, right? So they need to scale. They save money by taking it back and putting it back in. And that's a cool problem to solve. So now that we've got data in there, I'm not going to get too crazy on the read path. Again, just to make sure that we're keeping up with our time. I really want to leave a lot of time for questions, because I know that's where the meat of this usually lies. So I'm going to go through the reads here real quick. So reads are not a second-class citizen, and I think that's probably a perception because writes are so heavily talked about. We're talking about writes all the time, like, oh, you can do 1 million writes per second in your Cassandra cluster. But no one says, I want to do 1 million reads per second. It's just because writes per second have always been the harder problem. And reads are pretty much parity with writes. It's a different class of problem, though, completely. Now, I won't go into the single node semantics. There are some things there that I could get just as in-depth with it as a write. But essentially what you're doing is doing a single mutation. So we have this mutation that goes, the read goes to a node, and then that node has to figure out where the data is. Now this brings up the point of what's going on inside the cluster, and this is a good time to talk about things like consistency. So a client, your code, Ruby, CQ, or you can use Ruby, Python, Java, C++, plenty of clients out there. Go, we were just talking about Go earlier. The client's going to try to read data from the cluster. A client has this concept of a cluster built in. It's going to be aware of every single node. The client can ask any node, can I have my data? So let's say that it's looking for me, ID P. McFadden. Well, it may be that my ID is housed on node 1 as a primary because that's how it hashed out. The client isn't going to be thinking about that as much. It can ask any node the question. So any node can receive a read. What it's doing then, if I ask node number 4 definitely does not have the data because if it's a primary on node 1, node 2 and node 3 has the replicas. So if I go to node 4, that data is definitely not there. Totally cool. Because what we're going to do is node 4 is going to coordinate for the client. So when the client says, hey, give me ID P. McFadden, give me the first name for that, node 4 is going to say, got it. And it will go out and ask because it is aware. We have the tokens are not a secret. There's cluster awareness. It knows where that hash should lie. So it's going to go out and ask all the nodes, hey, do you have your data? Have this data? And coordinate for that. Once that response goes back to the coordinator totally fakes out the client and says, got your data. And it looks all cool. Like, look, I got your data. But really it's faking, and it went out and found the answer somewhere else. And that's how it works when you have downtime. If I ask node 4, node 4 crashed, the client would just stop and ask node 1, right back in action again. Because node 4 is not really, it'd be nice if node 4 was online, but if it isn't, we could deal with that. And I got some cool graphs to show you too. So that's how we keep the cluster online, is that no one's really that important. Now granted, we want to have all the nodes online, because it's not magic, but if you lose a single node, that should not bring down your cluster. As a matter of fact, you should be able to bring down any node during the day. Another cool thing that I found with Cassandra, when I ran Oracle databases, one of my all-time favorite things to do was negotiating downtime with our product managers. Hey, there's a really critical patch I need to get in here. And we'd all get on our calendars. All right, next month, Sunday at 3 a.m. Really? And that is exactly what the conversation went. So all my Oracle DBAs were pretty much vampires, right? Because they had to stay up when no one else was up. And then everyone expected them in the office at 8 a.m. That wasn't going to happen. So that was the world we lived in. I changed a lot of that moving to Cassandra because we were just rebooting servers during the day. Oh, wow, critical patch. All right, let's set it up. Let's do it. Got it. Okay, we can reboot. We can walk through our cluster and get it all done. All right, let's go grab a beer. It's still daylight. And you should be able to do that without having any downtime in your cluster. This should be a completely normal part of your day. And I like to think that we're giving DBAs daytime back. Isn't that nice? No more vampires, although some of them kind of want to be that way anyway, which is cool. We have a problem here, though. How do you know, from a client, how do you know who's going to ask, or how can you even specify what you want? So I teased this earlier. Consistency level. So replication factor, consistency level. That's the 1-2 punch. And this is what makes your application resilient and consistent, performant, all these good things that you want in your application. So consistency level is set with every read, every write. And you, as a application writer, can pick this every time you do a read or write, or you can just set a default, and that's fine too. So let's start with the bottom of the barrel, and that is 1. So in this scenario, I'm going to say, whenever I ask node 4 for data, I say, and consistency level of 1 is cool. It's going to just pick one of these and just ask, hey, do you got that data? And it'll be really fast. 1 is when you want to be fast. If you not have a coordination between multiple nodes, it's going to be a lot faster, right? It makes sense. So that is a pretty typical consistency level. And if you have a failure, it'll just go to another node. So the next one, which is this is the one that makes people who get antsy about consistency a little happier, and that is the quorum. And the quorum is probably where most people are. Quorum is 51% of those nodes are reporting back the data. So let's go back to our picture here. Let's say I have 4 nodes. I'm replicating my data, 1, 2, 3. 51% in this case is 2. 1, 2. Actually, I got a pretty picture of that. There it is. If I lose node 3, or I just turned it off because I wanted to do maintenance and it's 2 o'clock in the afternoon, cool. 51% of the nodes are still answering up. And node 4 says, got your data, and it's consistent. That is pretty reasonable when it comes to consistency. Now, quorum also has some checks and balances. If it finds data that's out of date or wrong, it can fix it. And that's also very helpful. Now, local quorum, and I know I'm going to get a lot of questions about this, so I'm going to leave time. Local quorum is in the case where you're across multiple data centers. And maybe you don't want to incur the WAN link time to satisfy the quorum. Pretty typical. If you're coast to coast, you're looking at 70 milliseconds of round trip, ping. So you may not want to add that. So local quorum just says, okay, inside this one data center, I want to have a quorum. And that's where, if you're in multiple data centers, that's probably where you're going to be. Local 1 is the same concept. Now, one of the things that's interesting about when you do a read of 1, 10% of the time by default, it's going to just do a quick check on the background. It's going to do what's called a read repair. And that just means that it does a quick consistency check. Because when you throw a 1 at it, you're kind of like, hey, give me my data. And you're not really doing any kind of quorum checks or anything like that, right? Well, a read repair is what gives you that assurance that potentially if I have outdated data or I have data that's inconsistent, that it will fix it. So that also crosses data center lines. Local 1 makes it so it doesn't. Again, keeping everything close. And that's kind of a new feature, largely driven by our users, right? This was contributed outside in Apache open source. So there's others like 2, just sounds, I bet you can't guess how many. How do you spell HTTP anyway? And then all. And this is what I call what your boss wants. But this isn't very practical. It's funny how many times I've been in design meetings and data, we're going to do everything in consistency all, because we want to be 100% consistent. And by the time we're done, and they actually run their POC, and they found out that quorum was totally fine, we never run all. But it is there. Now, there's one that I don't have on here, which is worth mentioning, which is in Cassandra 2.0. It's a new feature, so it's not experimental, but it is cutting edge and going through its paces right now. And that is the lightweight transactions. So when you set consistency, when you do consistency there's functionality like if exists. So you can see if a row exists before changing it. It also uses Paxos for locking. So you have exclusive locks on your data. So in cases where you might have a race condition between 2 processes mutating data, with Paxos, now that one process has an exclusivity over that row of data while it's mutating it. And then the other one's going to get rejected. That has been kind of a classic distributed systems problem of distributed systems. You are distributed. You don't know who's doing what. And with eventual consistency, you could have data overwritten without a good lock. People have been using Zookeeper and failing to make that work. Zookeeper is just more infrastructure madness, and I got a lot of bad Zookeeper stories, but I'm sure no one else does. Eliminating that and using something more ingrained in the database, like Paxos, makes sense. And so that's kind of a new thing. It's going to add to the consistency level. I would actually put it above all as more, a little crazier, a little more paranoid, let's put it that way, but also really useful. So this is a condition that we want to solve. I want to be able to bring a node down anytime. Good, bad, ugly, I want to be able to do this. And with your replication factor and your consistency level, you can do that. So what happens when this read happens, or you're doing a read and this node fails? Well, this is also I've done this with slave replication systems before, MySQL especially, where there's slave lag or change out time where my application stalls out for a minute or 2 until it figures out that one of the slaves is dead or something. That's really not a problem with Cassandra. And this is an interesting graph I feel, because this shows as we're hammering this cluster with 40,000 reads per second, I think it's a 5-node cluster, all of a sudden we kill one. Well, they take a little dip for just a second, and then they're right back at it. This little dip right here is where they're making sure that this one is offline and refiguring themselves. This didn't happen on the client. This happened on the servers. The coordinators did this. So the client is keenly unaware of this situation, which is awesome. Because the thing I hated the most was writing client awareness in my database failures. This should just be a feature. We should, as application developers, we should just write our code to a cluster that's going to be online all the time. And if it isn't, I'll be really upset. But I'm just going to assume that it is. And this is what it gives you, is that assumption is clear. So, hey, application programmers, let's finish up with some talk about CQL. So, I'm going to just kind of, I'm going to do a light introduction to CQL. If you want to go in depth with CQL, I have 3 hours of talks on YouTube. We also have a free online course in programming with Java using CQL and Cassandra. It's a 7-session course, 7 weeks, but you could probably do it in a week. And it goes in depth, and at the end, it's just like an online course. You take tests, you do projects, and there's plenty of resources out there to get you really in depth with this. So I'm going to give you enough to where you want to do it. And if you don't want to do it, I failed. So CQL, Cassandra Query Language. It's new-ish. Cassandra first started out on Thrift, and Thrift as an RPC is awesome for a lot of things. It's just not as good for some things. Where Cassandra wanted to go and what it needed to do, Thrift didn't cover all those cases because it's an RPC, right? It's stateless. CQL has changed that quite a bit into a more expressive language. And it looks a lot like SQL. So what's interesting about the table creation that I'm doing here is, yeah, sure, it looks a lot like what you would do with SQL, but it's not. Namely, notice that there's no sizing on here. Not a varchar 255. I could almost type that in my sleep. It's a varchar. The size of it is random and open, up to 2 gigabytes. And that's for every column that's inside here. So 2 gig column size just built in. Now, don't do 2 gigs, trust me. Because it's not going to be bad for the server, it's going to be bad for your application. Streaming 2 gigs of data into a single column, it's not going to pass any performance test you do. But it could do that, right? It's like, like driving a Maserati down the freeway. Sure, I could do 200, but 65 is cool too. Not really. 85, maybe. All right, I'll punch it once, right? I'll do like $1.10 for 5 minutes, then I'll be good. So I don't have a Maserati. I drive a Toyota. But anyway, so I'm safe. I like to call that the Mongo of cars. Ooh, did I say that? So the table creation up here that I'm doing should look familiar and expressive to your application. And that's what Cassandra is, an application database. It's built, really, it's an OLTP system. And so whenever you're modeling things like this, you should be able to express it easily in code. It gives you a table format, so rows and columns. And what we're hiding underneath the covers is the real good storage implementation that makes it work well. And hopefully you'll see that when you use it, that yes, I don't have to rethink about how the storage engine works. And like that write path that I showed you, cool to know about. But if you use CQL properly and you have a good data model, that's not really going to be your concern as much. So there's primary keys that can have multiple rows or multiple columns in it. And the insert statement looks pretty much like what I expect. So one thing I want to point out, though, is inserts will always overwrite. So there's little differences, right? For instance, inserts never do an existence check unless you tell it to. There is a way to say insert into users, and then if not exists. That's Paxos. Paxos will do a lock, make sure that it exists or not, then come back to the user if it does, and not insert that. You can do an exclusive type operation like this. But in normal, everyday Cassandra, it's an overwrite. So the insert and updates are kind of the same thing at that point. Now, there's different operations you can do with an update, like increment counters instead of overwriting them. But mostly inserts and updates are kind of the same operation when you get down to the storage engine. So we can do more advanced things with our data models. And this is what I talk about a lot. If you're planning on doing a project, I really encourage you to go watch my talks on data modeling. And not because I need more clicks on YouTube, because I don't get paid for that. It's because I'm talking to you, the application developer, on how to write CQL to match what you're trying to do in your application. And there's a lot of nuance, but it's not too bad. 3 hours of me. All right, so it's bad. Watch the first one, and if you can make it, try the second one. So this advanced part right here, let me explain what's going on. Like I have my uniqueness is this username and interaction time. I'm also controlling the ordering. Now, when I use SQL in Oracle, I used hints. You know, that's what all the cool kids did, right? Like, ooh, you're using hints. You must know a lot. Yes, I do. And it's because I knew what was going on in the storage engine. I knew how to game the query plan. Well, this is kind of along that line. It's a little more advanced, but what you're doing here is by ordering the interaction time here, the way that it's actually getting set up on disk is it's reversing the order. So now whenever I go ask for that data, I've set up this really interesting problem set where I can, and I'm going to show you how it works in a second, but now I can get the data out exactly the way I want it without having to go through any hoops. And I'll show you how in a second, by reversing that interaction time. So what this does is every time I insert into user activity a date stamp, that means the very first thing on that storage row is the last thing that happened. And it's in reverse temporal order. Another really cool feature that you can do with CQL is you can expire your columns. Right here, I want this data to expire after 30 days. That is a killer feature, especially if you have data that's somewhat transient, like user activity tracking. I don't want to have it after 30 days. It's dead to me. Or I've dumped it into a Hadoop cluster somewhere. I don't need it anymore. I need it now, not later. TTLs are basically free deletes. They are free deletes because once the TTL expires, that data is collected through the compaction process. So it just doesn't move that data anymore. Really cool. Now, how many of you have written that purge job in Oracle or MySQL? I wrote tons of those. Yeah, I got the... So what do? You turn off redo logs, you run your purge, and you turn it back on. Yeah, exactly, right? Well, this keeps you from ever writing that code ever again. I got some pain there, brother. Right on. We're going to talk later. So the purge job is solved by just expiring your data early on. I've seen some really cool use cases for this, like sessions, user sessions on web. You know, that's in seconds, by the way, right here. That right there. Funny little story. I like telling this story. And what's funny is the person I told the story about showed up at one of our trainings and said, you know what happened to me one time? And the trainer was texting me, said, oh my God, you weren't lying. It's real. I told you it was true. So here's the story. I was working with a very large grocery store customer, and they were doing mobile stuff using TTLs. The programmer and I were working. They loaded 3 million customer records into this database, and it was awesome. We were doing the work that we needed to do on their mobile site. I left. It was a 2-day engagement. About a day after I left, I get this email. Dude, all my data's gone. It's gone. What happened? I'm like, and we talked, and he's like, well, I rearranged some stuff. Maybe I blew it. I don't know. So, all right, we'll reload the data. Let's see what happens. 3 days later, get an email from the director. Cassandra sucks. I cannot believe we put this junk in our data center. It loses data. I can't believe what a toy this is. You guys really need to figure this out. Blah, freaking out. I'm like, what happened? Right? Because Cassandra doesn't lose data. I'm thinking, I said, did you guys set a TTL on the value? And I sent that email back. And about 10 minutes later, I get this real sheepish, oh, yeah, we set it for 3 days. So we didn't know what that feature was. So why don't you go ahead and use it, right? So they had set a 3-day TTL on every record, 3 million records. And what did Cassandra do? Right on time, like a train coming in the station, poof. And it's funny because they're really good users now of Cassandra, because now they believe in it. And they're like, oh, we use TTLs on everything properly. And it was funny because the programmer that did it showed up at one of our advanced training classes and relayed that story to the class. And the trainer was just like, oh, I thought that was a lie. I thought it was folklore. No, it's real. Anyway, so it's a funny story, but it illustrates the point is that it does work, and when used properly, it's really cool. So now that I reversed that data, and I'm almost done here, guys, so we can ask some questions. Once I reverse that data, whenever I select star from user activity and I limit it by 5, because I've reversed that order on the storage engine, the last 5 things that I get are the last 5 things that have happened. So in this case, this is my, my little make-believe. Well, not so make-believe. This actually happened somewhere, where we're watching activity on the website and we're trying to make determinations on it in milliseconds. It's a real-time analysis engine of making sure that you're watching user sentiment. You can see that things are happening, the last 5 things that happen, and then you can make decisions on those things really quickly and say, open up a shopping cart and closed it, things like that. Make decisions. So we have this data, very efficient. That can be rendered in a millisecond. That's real-time analysis. That is really cool. That's going to make your boss happy. It's going to make you happy. And it's all just knowing how to do those little tricks on the back end. So that is all my slides. And granted, I did not cover everything. Oh, not even. Not if I have 3 hours of talks out there. But I hopefully gave you enough to work with here to kind of whet your interest a little bit, tiny little bit, and ask some questions. I think this is a good time for questions. We have a microphone. Go ahead and hit me. I'm sure the first question is going to be about consistency. You have Mike. Who would like to ask? Oh, there we go. Mr. Delete down here. I love your shirt, by the way. Thank you. That's the kind of shirt I like. He's got the little Twilight diss. I like that.
So you've talked a lot about what's great about Cassandra.
Yeah.
What are some unique security concerns that come with setting up this distributed system?
Good question. And security has always been that kind of missing thing in NoSQL systems. Is like, oh, is that important? I mean, how many data Cassandra shipped for years without even having a username and password? Yep. But it was cool. That's no longer the case. When you go from just like basics, like being able to encrypt data, and so like Cassandra out of the box will encrypt communications using TLS or the SSL encryption across nodes, and then it also has a user control, so you have grant revoke, and so that's just out of the box. When you go to the enterprise side, we've even added things like encryption at rest and external authentication using Kerberos. So the security is, yes, a very genuine concern, and I think that's what's been addressed over the past year or two. It's no longer the case where you can set up a system that there's no possible way of locking it down. Hopefully that answered your question. Next.
I've got a question here.
Oh, we got a microphone too. Good.
Yeah, thank you. Yeah, thanks, Patrick. I just wanted to thank you on behalf of Cerner for coming out. I think everybody really appreciated this.
You got enough people out here? I'll come
I know.
again.
We packed the house today.
I'll come back.
So I have a sort of a philosophical design question. One of the things you cited early on was the Dynamo paper, and
Right.
I thought one of the more important aspects of that paper was the use of vector clocks to, you know where this is going.
I know where it's going.
But the use of vector clocks essentially to reconcile conflicts, and what I thought was more interesting was that when they ran into a semantic conflict, they would push it up to the application to do reconciliation.
Right.
So I'm interested to know what the design motivations were around, the use of physical clocks to establish order, and then, of course, a last right wins method of reconciliation of conflicts.
Yeah, and then if you look at the original Cassandra paper, there was some discussion about the removal of the vector clock ideas. Basically, One, it was a matter of performance. And so, that's kind of where it comes down to, is vector clocks. And if you look at the Apache Jira for Cassandra, there's been several times where we've talked about should we not, and it really comes down to performance. And pushing that back to the client is a trade-off that you can hopefully manage with consistency guarantees, if you have that, and also just the semantics of LWW. Yes, there's a little more operator because you're relying on clocks. Those clocks have to be synchronized. And sure, you can get in big trouble if your clocks are not in sync, because that timestamp is really important to the entire system. Where vector clocks might fix that, it's not actually, if you have out-of-sync clocks, vector clocks will make it very hard for the client to deal with. You'll have orphans after a while. But I think it's just been a philosophical decision that performance is going to trump out. A million writes per second is important. Now, if you need that, here's LWW. Here's how to manage it. It's like anything else in computer science. Make sure you know all the rules, make sure you have all the semantics, and then apply your methodology to it.
Yeah, just a quick follow-up. I think, and I completely support that and I understand that. I think the challenge that a lot of people have with many of the distributed storage systems that have, that are open source today is they don't understand those trade-offs, and so they make decisions about how they design their systems with the wrong set of assumptions. So when you do end up in a situation where you have an unexpected, a last write wins scenario will wipe out a previous write, that's where you really get into trouble. So it would be, and so I think focusing on understanding what the actual trade-off is for using Cassandra will help engineers understand how to apply that to their real business situation.
Well, it's interesting because eventual consistency has always been a problem. A lot of the original papers for eventual consistency were from IBM because they were distributing systems or distributing data on really slow links. One of my favorite papers is your bank is not consistent. Banks are eventually consistent. If you go to Jamaica and take out money out of 3 ATMs and you overdraw your account, it'll probably work, but they'll catch you. Banks and credit card companies have a profit model based on eventual consistency. It's called overdraft fees and overcharge fees. And so this is, and they understand it to the point where they're making money, right? Well, in the case where you have like a system where you can't afford that, how do banks manage that? I mean, they're not going to lose money, right? They're not going to lose data. So how do they manage that? One of the techniques is using a ledgering type system. And I've worked with financial services companies. Financial services companies love Cassandra because it will stay online. Now that it's online all the time and we can do things at high rates, how do we manage it? Ledgering is one of those things. With vector clocks, you're expecting to update the same value over and over and over. With ledgering, you're using the semantics of Bigtable so that you can write independent values and keep track of everything that's happened inside the database. It's similar in a lot of ways, but what you wind up getting is that fast write speed without having to worry about it kicking back an orphan to the client and saying, figure it out. And that's the performance guarantee. So you can manage that yourself, but that's something you have to manage yourself with, like a ledger. Boy, we're getting really into the depth. I like that. And data modeling is the key. That's why I spent so much time talking about it. A good data model will take care of this. It's just good science. Next question. Down here.
I noticed that Cassandra shares a lot of similar features with the HBase, the Hadoop HBase. So I wonder, what, can you make a comparison with them? And I think the Cassandra is more like a very symmetric system. So every node has the same they are created equally, but in the HBase, they focus on more has a master stuff, and so you can make some range scanning. So I wonder in the Cassandra if you can do that, and also like does Cassandra support map reduce?
Mm-hmm. Okay, so HBase, yeah, so they're really close cousins because big table. And HBase, I've run HBase in production. It was on top of my Hadoop system, surprise, and Cassandra in the same environment. So I do have a little point of comparison. So they semantically varied same in one row key, lots of columns, right? That's very similar. Beyond that, there's a lot of, that's when they kind of depart. And you're right. So when you set up HBase, you have region servers, Zookeeper to manage all of that, and you have the sequential access. And it's really based on HDFS, right? So that's where your data resides. A lot more operationally complex, for sure. And you're right, with Cassandra being every node is created equal, it makes it really easy to run a Cassandra cluster because you bring up a node, it automatically participates in the cluster, you decommission it, it leaves. There's just not a lot of problems. I think that was my first impression of the differences is just operationally. Running HBase versus Cassandra. Cassandra is a lot easier to run. One of the funny things that Cassandra people that have been doing this for a while talk about is how bored they are. Because Cassandra cluster, once you get it up and running, it just works. There's a guy that was on my evangelist team. He worked at Uyala, wound up leaving. His Cassandra cluster had been up for 3 years. Never had an outage. 100% uptime for 3 years. So, and it's just because it was easy. They used Chef. You know, everything was automated. They were a knife command away from everything. So it was just an easy setup for them. Now, HBase does have some advantages in sequential data because everything is sequential. It uses an ordered partitioner instead of a random partitioner, which is, you know, when you're doing ranges and things like that. But again, with Cassandra, there's a different data model for that. And I think when I was doing Cassandra work with Thrift, it was very similar to how you interface with HBase, you know, Avro. And now I think that's departed some. The programmer model, HBase versus Cassandra, much different. HBase doesn't have anything like Cassandra as query language, CQL. So you can't do table type semantics, you know, row, column, that sort of thing. So I mean, it depends on which direction you're looking at. Operationally, less complex. Programmatically, more expressive, I feel. Now, MapReduce, granted, HBase is going to be great, right? Because it's sitting on top of HDFS. There are MapReduce frameworks. DataStax, we sell a MapReduce. We put Hadoop on top of column families with the tables. So as table data is getting ingested, we can do MapReduce on that. We also are supporting a way that you can plug in your external Hadoop cluster and analyze data directly on Cassandra. So I think that's a given anymore. If you can't analyze data with Hadoop, then you're not in the game. But we also add Solr on top of that as well. And soon other MapReduce type, I would say an analytic workload generator without using MapReduce. And I'm sure you can guess it's probably Spark. There's some really cool talks on using Spark and Shark with Cassandra. Because it's very similar. And it's a lot faster than Impala. That's sure. I think I got all of yours, didn't I? You had like 10 questions in one. Any more? There we go.
So you talked about how multiple records are merged into one record. Mm-hmm. So when old records are merged into a new record, and you delete the old records, does that like result in a random I/O versus a sequential I/O?
No, it does not. Here, let's go back to that slide. Hang on. I'm glad somebody asked about compaction, because compaction is one of those things that's like, really, how did that work? So in this case where we have two files with one row of data and then an older row of data, so duplicates basically, right? That situation just means that when the query parser runs, that it has to make the choice for you. So you're still doing a SS table read is still a random read. That's the only random operation, I/O operation on Cassandra, is when it has to look for this one row of data. And that's an indexed operation on the SS table. So it will, oh, I'm looking for this row of data. Here's an index that'll take me right to it in the SS table. So it's still random, though, because it's not going to read the entire SS table. Because sometimes these SS tables can be gigs. We're not going to read the whole thing. So that random read, it's going to have to do those 2 random reads to find that data. That's uncool. The compaction process sequentially reads all of that row data in, both files, so it's sequential, both files, reads them into memory again, merge sorts in memory, and then sequentially writes that data back out into a single file. So if, let's say you had 2 1 gig files, and it merge sorted those, the resulting file may be 1.5 gigs. Some of that data got removed because it was old. Some of it stayed because it was perfectly fine. So the compaction process is definitely sequential. Sequential read, sequential write. And also one that really needs to be paid attention to. Because if you're not keeping up with compaction, you have the situation here where you're going to be doing a lot of random writes on useless files. Compaction is it's like defragging your disk. Man, my dad used to do that every day. Like, you don't need to do it every day. But in this case, you kind of do. Because your data, especially when your data is moving in really fast, compaction runs automatically. Just let it run. But it needs to be able to keep up, which means that your disk system needs to be able to deal with this. Shared storage on a Cassandra system is a recipe for failure because it doesn't do sequential I/O very good. And the EMC guys hate admitting it, but it's true. Shared storage is great for random I/O, but it's terrible at sequential I/O because it just burns out the arrays. I've seen an EMC array almost melt based on a Cassandra load. So the sequential read, sequential write, no more random operations. Yes? I got 1 minute or one more question? One more. One more question. Who's going to have that magic question? There's got to be one more burning question in here. I didn't get anything on consistency.
I'll ask the last question. Actually, somebody's got one down.
All right, got one down here. All right.
So let me ask the question you were trying to get to.
Thank you. Here's your $20.
With the local quorum, what happens if something outside of the local cluster has a later timestamp and different data?
Good question. Now, if it has a later timestamp, so if this cluster has Pat and then the other, it's not a cluster per se, it's a data center. Let's get our semantics right. If one data center has Patrick and one data center has Pat, right? That's what you're saying? Now, because you're using a local quorum, you're just asking for the guarantee for the client. When the client asks, hey, can I get this data or set this data at quorum or local quorum, I only want a response from inside that local data center. What that doesn't mean is that it won't go to the other data center. It's still going to do it. It's just not dependent on how fast you get that response acknowledgement back from the coordinator. So, and that's a good point to make. It doesn't just drop it to the floor and say, oh, we'll do that later. And that doesn't happen that way. It will still do that. Now, let's say that bad things happen, like the WAN link went down. Someone put a backhoe through the WAN link. That's happened to me a couple of times. So you have a split brain. This is where the CAP theorem comes in. And CAP, of course, is consistency, availability, partition. Cassandra is partition tolerant, but you can also change that. You can make it completely partition intolerant by saying all. But if it's partition tolerant, local quorum means that even if I don't get a response from that other data center, my application's still online. Now, there's semantics built in. There's stuff built into Cassandra from the Dynamo paper too, that once those become aware of each other again, that they will repair and move data across. So there's a manual operation called repair, then there's an automatic called hints, and those get stored on either side. So consistency, there's plenty of ways to keep consistency going, and there's just layers to that. But it's always the name of the game, is making sure that you have consistency and just dealing with being able to manage all the problems that could potentially happen. All right. That was it. No more questions, huh? All right. Good deal. Thank you very much.